So I'm reading through Structure and Interpretation of Computer Programming. What did I found this sort of syllabus or whatever on GitHub, which links some lectures from Berkeley, and basically it's organized into like read a section of SICP, Structure and Interpretation of Computer Programming, and then watch a lecture. And then here I've got DrRacket open, and I read that basically these magic words are, they load up like a scheme profile that you can use for doing SICP stuff. So that's what I'm going to do. Okay. One easy way to get started at programming is to examine some typical interactions with an interpreter for the scheme dialect of Lisp. Imagine that you're sitting at a computer terminal, you type an expression, and the interpreter responds by displaying the result of its evaluating that expression. One kind of primitive expression you might type is a number. More precisely, the expression that you type consists of numerals that represent the number in base 10. If you present Lisp with a number, 486, and I've already done this, but I'll just do it for the video. Oops. I was in the wrong place there. Yeah, so type 486, and I got back 486. Expressions representing numbers can be combined with an expression representing a primitive procedure, such as addition or multiplication, to form a compound expression that represents the application of the procedure to those numbers, for example. Yep. Right, and so this is subtracting 334 from 1,000. So no surprises there. Expressions such as these, formed by delimiting a list of expressions within parentheses in order to denote procedure application, are called combinations. The leftmost element in the list, that would be like the plus or whatever, minus, yada yada, is called the operator. And the other elements, which is the 10, the 5, the actual numbers, are called operands. The value of a combination is obtained by applying the procedure specified by the operator to the arguments that are the values of the operands. And so just like addition can take, I would guess, any arbitrary amount of arguments, but right, so that's interesting. So addition works pretty straightforwardly, but it seems like division, like you start, like it seems to be doing like 500 divided by 5 is 100. And then 100 divided by 2 is 50. Keep going down there for some reason. I guess that's if I want to search for stuff. All right. So oops. Yeah. So it seems like if you it seems like the way these operators, the like basic math operators work, it must be like recursive or something, I think. I might be getting a little out of my depth here already. But like it seems like it takes the first two numbers and does the operation in a straightforward way. And then like you would expect, like if I just said that, that's pretty clear what's going to happen. You should expect it's 5 minus 3, so then you get 2, right? And then it says, okay, so now we have 2. So now we're going to take that 2 and we're going to plug it in and use the other 2, because remember there was already a 2 up here. So this is the 2 that's from this, and then this is the 2 that was already there. It's not a great example to use the same number, but I mean I get it. So these aren't educational videos really, except for me. So I think I follow the example. Um, so then you get 0, and that's where we wound up, is 0. Okay, so that makes sense. The convention of placing the operator to the left of the operands is known as prefix notation. And it may be somewhat confusing at first because it departs significantly from the customary mathematical convention. Prefix notation has several advantages, however. One of them is that it can accommodate procedures that may take an arbitrary number of arguments, as in the following examples. Right. So you don't have to, so they're saying an advantage basically is like, you don't have to, if you want to multiply 25 and 4 and 12, you don't have to do 25 times 4 times 12. You just get to write the thing once. Now, of course, if you want to do different stuff, then I would imagine you just like do that. Like if you want to multiply 25 and the result of 10 and the sum of 10 and 3, which, what's that going to be? Is that like 325? Yeah, okay. Then I don't know why I'm like nervous about getting mental math right on my like videos that 10 people are going to watch, but whatever. That's that's exploring that issue is maybe a different video. Um so right, so yeah, my point was like the way this sets it up, you can, with the prefix notation, you can just input as many numbers as you want and have it perform the operation. And then if you want to do a different operation, you can just specify that particular operation. So say no ambiguity can arise because the operator is always the leftmost element and the entire combination is delimited by the parentheses. Yeah, no, it's pretty clear like what's supposed to happen. The second advantage of prefix notation is that it extends in a straightforward way to allow combinations to be nested, that is, to have combinations whose elements are themselves combinations. Right, so I was doing some nesting here. Let me see. And I guess, yeah, you start with like the nested stuff. Like the order of operations is you start with like the nested stuff and then you work your way up. There is no limit in principle to the depth of such nesting and to the overall complexity of the expressions that the list interpreter can evaluate. It is we humans who get confused by still relatively simple expressions such as this mess. Which the interpreter would readily evaluate to be 57. Yep. We can help ourselves by writing such an expression in the form. And so then, yeah, they're using indentation to make clear like what level stuff is on. It's A, and then you add those. Yeah, it's still like, I still find it a bit tricky. Because it's like a lot of, it's also like I would find just normal, like a normal order of operations, like conventional math notation, a bit easier to read in a way because I'm used to it. So they say following a formatting convention known as pretty printing, in which each long combination is written so that the operands are aligned vertically. Resulting indentations display clearly the structure of the expression. That's the footnote. There's already been a bunch of footnotes. This is kind of a long one. I want to go back to this one. Where is it? In this chapter, we will deal only with simple numerical data so that we can focus on the rules for building procedures. The characterization of numbers as simple data is a barefaced bluff. I like that they're sort of flaming their own writing. Well, that's kind of funny. In fact, the treatment of numbers is one of the trickiest and most confusing aspects of any programming language. Some typical issues involved are these. Some computer systems distinguish integers such as 2 from real numbers such as 2.71. Is the real number 2.00 different from the integer 2? Are the arithmetic operations? Well, let's. Right, so I see the issue. Like conceptually, like a human can say 2 is the same as, 2 with trailing zeros, off into infinity. But if a computer is distinguishing these two numbers, then yeah, because it's like this will have a different representation than this. Like there's it's like a different number of characters and stuff, So you can't just. So then if you want to say they're the same, you've got to figure out some like rule for when to treat them the same, and then like you could say, well, an integer is the same as 2.00 to some number of zeros. But then you've got to figure out, okay, but then how many zeros do you check and how many do you store? So yeah, I could kind of see the issue. Like it's it's a bit beyond me, but I can like vaguely intuit some problem there. So are the arithmetic operations used for integers the same as the operations used for real numbers? Okay, that. Oh, is this the same? The 6 divided by 2 produced 3 or 3.0. Okay. So I think, are these all separate questions then? Because I'm not sure if these are supposed to be related. So I'm just gonna, I think this is like a separate question. I don't really get this one. Are the arithmetic operations used for integers the same as the operations used for real numbers? I don't know quite what they have in mind there. This 6 divided by 2 produced 3 or 3.0. Right. So this is sort of going back to this one. Like that, there's a similar set of issues there. How large a number can we represent? How many decimal places? Yeah, because if you like if you put if you like take a number to some power on some like calculator, eventually it like beeps at you if you just keep raising it. So there's a limit. Right. That actually happens pretty fast, even on like a computer calculator. Like I mean all calculators are computers, but I mean this is this is not Texas Instruments. So we're just squaring 10. See? It's like, nope, I'm done. So that didn't take long at all, you know. How many decimal places of accuracy can we represent? Right, right. Those. How many? Is the range of integers the same as the range of real numbers? Above it, well, is the range of integers the same as the range of real numbers? I'm not sure. Range of data set is the difference between the largest and smallest numbers in each data set. I'm not sure if this is the right. Because like, oops, where'd it go? I'm gonna move this one to the first position so I can find it easy. Okay. Not sure what this one is about. I mean, because like the reels have like more. Like there's more real numbers in like 1 through 10 than there are integers in 1 through 10, but they're both like infinite ranges, I think. Okay. Well, I don't want to focus too much on this because this is that it's I am trying to understand roughly the point of each question, but I may not be able to sort out good answers to every one of them, and I think that's fine. Above and beyond these questions, of course, lies a collection of issues concerning round-off and truncation errors, the entire science of numerical analysis. Since our focus in this book is on large-scale program design rather than on numerical techniques, we're going to ignore these problems. Okay, me too. The numerical examples in this chapter will exhibit the usual round-off behavior that one observes when using arithmetic operations that preserve a limited number of decimal places of accuracy in non-integer operations. Okay. So they're saying usual round off behavior. So they just round stuff off typically, and they're gonna, I guess, sort of a convention or customary way of rounding stuff off that they're gonna follow, I guess. Okay, so let's jump back up. Well, actually, which one was I on? Right. List systems typically provide features to aid the user in formatting expressions. Two especially useful features are one that automatically indents to the proper pretty print position whenever a new line is started, and one that highlights the matching left parentheses whenever a right parentheses is typed. Yeah, no, that's especially useful. Okay. Even with complex expressions, the interpreter always operates in the same basic cycle. It reads an expression from the terminal, evaluates the expression, and prints the result. Read, evaluate, print. This mode of operation is often expressed by saying that the interpreter runs in a read, eval, print loop, or a REPL. Observe in particular that it is not necessary to explicitly instruct the interpreter to print the value of the expression. What's this? Okay. A critical aspect. Okay, so section 1.12. Naming in the environment. A critical aspect of a programming language is the means it provides for using names to refer to computational objects. We say that the name identifies a variable whose value is the object. Say that the name identifies a variable whose value is the object. In the scheme dialect of Lisp, we name things with define. Typing define size 2 causes the interpreter to associate the value 2 with the name size. Once the name size has been associated with the number 2, we can refer to the value 2 by name. Now let's try it. Pause the video for a second. So already did it, but just see that it'll change. Right, so just do define rather, size, whatever. And then you say size. And you get the value back. And if you do it again, you change the value to whatever the last thing you said it was. It's a number, we can do number stuff. Right? Since I did size 10 and I multiplied size by 5, I got 50. So they're giving further definitions of further examples of define. You define pi, radius, etc. Define is our language's simplest means of abstraction, for it allows us to use simple names to refer to the results of compound operations, such as the circumference computed above. So I just entered this stuff, and I had an interesting thing, so I typoed this as or I should say this as one word, and I got asterisk pi undefined cannot reference an identifier before its definition. So, like the computer knows what it's supposed to do when you say define something as something. It's like it's expecting a couple of arguments. And then when you define that something, it knows the value of that. But when I typoed, the computer looked for, instead of looking at um, operator and then pi and then figuring out what the value of pi was, it looked for this whole thing as like an operator or to see if it had a value or whatever. And it didn't find anything for that. So then it's like, well, this is undefined. What are you doing? So, because I typed in the wrong thing, and so it couldn't find anything matching that. So this says define is our language's simplest means of abstraction, for it allows us to use simple names to refer to the results of compound operations, such as the circumference computed above. In general, computational objects may have very complex structures, and it would be extremely inconvenient to have to remember and repeat their details each time we want to use them. Indeed, complex programs are constructed by building, step by step, computational objects of increasing complexity. The interpreter makes this step-by-step program construction particularly convenient because name-object associations can be created incrementally in successive interactions. This feature encourages the incremental development and testing of programs, and is largely responsible for the fact that a Lisp program usually consists of a large number of relatively simple procedures. It should be clear that the possibility of associating values with symbols and later retrieving them means that the interpreter must maintain some sort of memory that keeps track of the name-object pairs. This memory is called the environment, more precisely the global environment, since we will see later that a computation may involve a number of different environments. Chapter 3 will show that this notion of environment is crucial both for understanding how the interpreter works and for implementing interpreters. Okay. One of our goals in this chapter is to isolate issues about thinking procedurally. As a case in point, let us consider that in evaluating combinations, the interpreter itself is itself following a procedure. To evaluate a combination, do the following. Evaluate the sub-expressions of the combination, right? So that's what I was talking about earlier, where you start from like the innermost. Apply the procedure that is the value of the leftmost sub-expression. Oh, I see, this is even. So like, it's that example I gave before. All right, this like long one, or even, I mean, we could just even think of a simpler one. So evaluate the sub-expressions of the combination. So like, I think you even start like, okay, so there's this whole thing, but then it has a sub-expression. And actually, this sub-expression has its own sub-expressions. And you've got to go, okay, so sub-expression 1, this is what, so then it gets all the way down. It's like, okay, so in this nested thing here, this first value is 10. And then this next value is 3. Those are the values. And so you evaluate that, and they say, okay, then apply the procedure that is the value of the leftmost expression, the operator. So here it's addition, to the arguments that are the values of the other sub-expressions, the operands. So you do, you add 10 and 3, and then you repeat. So then you've got 13, and then you say, okay, so we've got this thing, but now this is 13. So then we've got this first expression here is 25, and then the new expression, this would be 13. And then what do we do with those? We multiply them. Even this simple rule illustrates some important points about processes in general. First, observe that the first step dictates that in order to accomplish the evaluation process for a combination, we must first perform the evaluation process on each element of the combination. Thus, the evaluation rule is recursive in nature. That is, it includes, as one of its first steps, the need to invoke itself. Right, and so the reason this is recursive is because, like, step one is evaluate the sub-expressions. Now, in a simple case, the sub-expressions might just be like 2 and 2. And then you apply, or I made a bit of a misstatement because I just realized, because I'm treating the operators differently, but they're just sub-expressions too. Like this expression, I guess, at least the way they're treating it, I think it's fair, has like 3 sub-expressions. The minus, the subtraction operator, the first value 2, and the second value 2. And so it's this method of evaluation is recursive, or this structure is recursive, this procedure, whatever you want to call it, because in order to evaluate the sub-expressions of a combination, it has to be able to get like a value from them. So like if you have something like this, it's pretty easy because everything is just already like finished. But if you have something like this where there's some nesting, then the procedure is basically, okay, well, we can evaluate the first sub-expression, which is the operator, and then we can look at the first argument, and that's fine, that's 25. So we've got the first sub-expression is multiplication, the second sub-expression is 25, but then we get here and we're like, uh-oh, what are we going to do? We have to look at what this actually is. So then evaluating the sub-expressions of the combination involves sort of going under the hood here and looking at this nested thing. And then we can apply the same thing where we say, okay, well, let's evaluate the sub-expressions of the combination. And then we go, okay, well, there's the addition, and then we have this first argument here is 10, the second is 3. And since there's no more nesting, then we can go to step 2, which is apply the procedure that is the value of the leftmost sub-expression to the arguments that are the values of the other sub-expressions. So that's fine. So the base case for this recursion is like when there's no more nested expressions, basically. When you just get to the basic sub-expressions. But it is as recursive because it does keep going into the nested levels of the expression, that any expression you look at, if they exist, until it can evaluate all the sub-expressions, and then you sort of work your way back up. And I've looked at stuff regarding recursion, and like I'm talking about the base case and all that. Like I've looked at some of that type of stuff before. So I have some prior knowledge here, but it's still good to talk through it explicitly because it's been a while. So yeah, where was I? They said, first observe that the first step dictates that in order to accomplish the evaluation process for a combination, we must first perform the evaluation process on each element of the combination. Thus, the evaluation rule is recursive in nature, right? Because it's saying, step 1, evaluate the subexpressions. Step 2, apply the procedure of the operator to the arguments. And step 1, I guess, is really what sort of carries you over through the nested levels until you get to no nesting, and then you can go to step 2. Notice how succinctly the idea of recursion can be used to express what, in the case of a deeply nested combination, would otherwise be viewed as a rather complicated process. For example, evaluating this expression requires that the evaluation rule be applied to 4 different combinations. We can obtain a picture of this process by representing the combination in the form of a tree, shown in figure 1.1. Let's look at figure 1.1. Okay. So they're giving us a little graphical representation. And so this is showing like the nesting. And this is cool because, let me zoom out of it. Because this is helpful because it's showing you the levels of nesting a bit more clearly than you might get just from looking at this and like how deep expressions are. Like I've been dealing. Excuse me. I've been dealing with some nested stuff in another context in learning grammar, and it's good to have these diagrams because they're just a different way of representing the information that can be useful for understanding exactly where stuff is. Because it can be kind of hard, even if you've got it on different levels like this, where it's not all on one line. It can still be kind of hard to just intuitively grasp like how deeply nested stuff is. So each combination is represented by a node with branches connecting the operator and the operands of the combination stemming from it. Right, so they've got like 4 and 6 are the most, 4 multiplied by 6 is the most deeply nested thing, so that's at the bottom, and they've got the branch, and they're putting the result of running the procedure at the nodes or whatever. Right. So the terminal nodes, that is, the nodes with no branches stemming from them, like these or these or these or these, represent either operators or numbers. Viewing evaluation in terms of the tree, we can imagine that the values of the operands percolate upwards, starting from the terminal nodes and then combining at higher and higher levels. That's a different way of what I was thinking. Like, you go down to the lowest level and then you do the operation and then you can go higher. So since this is like the deepest node, this 4 and 6 being multiplied, you could kind of start there, and then you get 24, and then you can add that to 2. And, so you sort of work your way up. You get to the bottom, and then you work your way up. And that's what the computer does. In general, we shall see that recursion is a very powerful technique for dealing with hierarchical tree-like objects. In fact, the percolate values upward form of the evaluation rule is an example of a general kind of process known as tree accumulation. I have not heard that terminology before. Next, observe that repeated application of the first step brings us to the point where we need to evaluate not combinations, but primitive expressions such as numerals, built-in operators, or other names. We take care of the primitive cases by stipulating that the values of numerals are the numbers that they name. And so the value of 3 is 3, the value of 5 is 5. The values of the built-in operators, those would be like the plus, multiplication, are the machine instruction sequences that carry out the corresponding operations. What is that? So, it's just the value of like plus is whatever code the computer runs to combine, a 2 and a 4 or whatever you give it. And the values of other names are the objects associated with those names in the environment. Right, so if we define, we define size as 5, then size is the value of 5. We did that earlier. We did like define size 10. And so then we could multiply 5 by size and we got 50. We may regard the second rule as a special case of the third one. What are they saying here? They're saying, by stipulating that symbols such as plus and multiply are also included in the global environment and are associated with the sequences of machine instructions that are their values. Oh, I see. So they're just saying that basically the values of, you kind of say the value of anything are the objects associated with, the value of any name is whatever you associate it with it in the environment. And so the built-in operators are just like what's associated with, like what the computer does when you tell it add is just a value that's associated with it in the scheme environment. So you could think of it like that. So, but those are just sort of like given to us. Like we don't have to define how to add stuff. Those are just given to us by the programming language so we can start doing stuff and playing around and learning. But you could think of this as like a case of this. The key point to notice is the role of the environment in determining the meaning of the symbols and expressions. In an interactive language such as Lisp, it is meaningless to speak of the value of an expression such as add x and 1 without specifying any information about the environment that would provide a meaning for the symbol x or even for the symbol plus. As we shall see in step, so that's interesting. Right. So they're just saying like because we can define x to be whatever, like this has no inherent value. I mean, we could even redevalue. We could revalue like the numbers even if we wanted to for some purpose. Like we could tell the computer, okay, if I type 1, you treat it as 2 or whatever. Like I don't know why you'd want to do that, but you could. But certainly for stuff like x and even for stuff like plus, you have to like the environment has to tell you, or you have to tell the environment has to have some value associated with those. There's no inherent meaning here. There may be like there are certain defaults set up in a particular environment, but those are malleable. Notice that the evaluation rule given above does not handle definitions. For instance, evaluating define x3 does not apply define to 2 arguments, one of which is the value of the symbol x and the other of which is 3. Since the purpose of the define is precisely to associate a value x with a value. Right. Right. So the purpose of this thing we were talking about is like how does the interpreter evaluate a combination? And so it like figures out the values of stuff and applies procedures to stuff. But define puts a value on stuff. So that's not within the scope of this evaluation rule. Like the evaluation rule can take something like size and multiply. Like if we give size a value, it can take it and multiply it by 5 or add it to 2 or whatever we want to do. But the actual assignment of that value, giving size a value, is not within the evaluation rule scope. That's all they're saying. Such exceptions to the general evaluation rule are called special forms. So that's a pretty high level definition of what a special form is. So like they're just saying, this is like the default, and then if you're doing something else, then that's a special form. Define is the only example of a special form that we have seen so far, but we'll meet others shortly. Each special form has its own evaluation rule. The various kinds of expressions, each with its associated evaluation rule, constitute the syntax of the programming language. In comparison with other programming languages, Lisp has a very simple syntax. That is, the evaluation rule for expressions can be described by a simple general rule together with specialized rules for a small number of special forms. Okay. So we have identified in Lisp some of the elements that must appear in any powerful programming language. Numbers and arithmetic operations are primitive data and procedures. Nesting of combinations provides a means of combining operations. Definitions that associate names with values provide a limited means of abstraction. Now we will learn about procedure definitions, a much more powerful abstraction technique by which a compound operation can be given a name and then referred to as a unit. So far we were just associating, when we did define size, we were associating this with a value, but now they're going to show us about associating like a name with doing a thing with values, doing a thing with arguments, doing something. So we'll get to make our own like operator, basically, like our own multiplication or addition or something. We begin by examining how to express the idea of squaring. We might say to square something, multiply it by itself. This is expressed in our language as define square x, and then multiply x times x. I just did that, and I made the square definition. So yay. So we can understand this in the following way. It says define is 2 square something, multiply it by itself. Okay. We have here a compound procedure which has been given the name square. The procedure represents the operation of multiplying something by itself. The thing to be multiplied is given a local name x, which plays the same role that a pronoun plays in natural language. Evaluating the definition creates this compound procedure and associates it with the name square. The general form of a procedure definition is define, name, formal parameter, body. The name is a symbol to be associated with the procedure definition in the environment. The formal parameters are the names used within the body of the procedure to refer to the corresponding arguments of the procedure. The body is an expression that will yield the value of the procedure application when the formal parameters are replaced by the actual arguments to which the procedure is applied. All right, so this part is just like kind of naming stuff. Like we give the procedure a name, and when we call the procedure, we're going to give some arguments. Like when we call square, we're going to give it a number. We're going to feed it a number to square. So we're basically calling the number that we give square x, and then the body of the procedure is where all the stuff happens. So that's where. So our procedure is now named, and we've said what we're calling the parameters. So now we just do whatever we're going to do, using like to our arguments that we're going to feed it, and we use the name of the formal parameters. And then they're just using square sum. You can also use square as a building block in defining other procedures. For example, x squared plus y squared can be expressed as the sum of square of x and square of y. We can easily define a procedure sum of squares that, given any two numbers as arguments, produces the sum of their squares. Now that's pretty straightforward. Now we can use sum of squares as a building block in constructing further procedures. Define f of a. Right, so and I just did this. Basically, you can use the sum of squares, and then you can define a function that if you give it a number, it figures out, it takes that number, adds 1 to it, and then that's this x, and then it takes that number, multiplies it by 2, and that's this y, and then it gives you the sum of the squares of those two resulting numbers. So, and the point of this is just to show you how you can just, like, you can build and build and build, and you can kind of you can build up this like tower of procedures, and you don't have to remember exactly all the details of, although these are pretty simple. So when it's introductory, so it makes sense that it's simple. But like you could just keep building on top of lower levels, and then you don't have to worry so much about the lower levels anymore because those are built, those are fine, and so you can just focus on whatever you're trying to do right now. Compound procedures are used in exactly the same way as primitive procedures. Indeed, one could not tell by looking at the definition of sum of squares given above whether square was built into the interpreter, like addition and multiplication, or defined as a compound procedure. The substitution model for procedure application.